In this lecture, we'll discuss the Fourier transform of sinusoidal functions. In the previous lecture, we have seen that the Fourier transform of cosine and sine functions can be expressed in terms of the Dirac delta function as, and for a sine wave, we can write the Fourier transform in terms of delta functions as this. And we have seen that the Dirac delta function can be considered as a limiting case of a rectangular pulse with a pulse duration of a and an amplitude of 1 over a, and the delta function is the limiting case of this rectangular pulse in the limit that the pulse duration tends to 0 and the amplitude tends to infinity. We have also seen that the delta function can be represented by the sinc function with an amplitude dependent upon the parameter omega, and as omega tends to infinity, that is, the amplitude tends to infinity and the width of the sinc function tends to 0, we get the delta function. So in this plot of this function over here, the width is inversely proportional to omega and the amplitude is directly proportional to omega. So in the limit that omega tends to infinity, pulse duration shrinks to 0 and its amplitude tends to infinity, while still the area under the curve is 1, and therefore we recover the delta function. So we have seen these two representations of the delta function in the previous lecture. So while deriving the Fourier transform for sine and cosine waves, we had used the properties of the delta function to arrive at the Fourier transform of the sine and cosine waves. So essentially, the Fourier transform of a cosine wave consists of two delta functions at frequencies of minus omega naught and omega naught. Such as this. In this lecture, we'll revisit the problem of the Fourier transform of cosine and sine waves, but with a different approach. The idea is to provide you an insight into the representation of Fourier transforms of sine and cosine waves, and that representation can be provided through the example of a pulse-modulated cosine wave. Consider this pulse-modulated cosine wave, which is given by the function f of t, and this function is given by cosine omega naught t with an amplitude of a for a time interval of minus capital T to t, and this function is 0 for all other times. That means if we have a cosine function with a frequency of omega naught, we'll consider only that part of the cosine function which lies between the time intervals of minus t to t, and outside this interval we'll consider that the function has zero value. So this is what we mean by a pulse modulated sinusoidal function, and in this particular case we have a pulse modulated cosine function with frequency omega naught and an amplitude of a. So this function is non-zero only between the time interval of minus capital T to t. So the idea is to evaluate the Fourier transform of this pulse modulated cosine function, and note that this function that is defined for minus t to t is absolutely integrable, because the integral given by this takes on a finite value, because this function is non-zero only between times minus t to capital T. But if we consider the limit of t tending to infinity, we'll arrive at the Fourier transform of the cosine function. So the idea is we'll begin with the Fourier transform of this pulse modulated cosine function and then take the limit of t tending to infinity. So let's do that calculation. So the Fourier transform is given by this integral and because the function is non-zero only between the time intervals minus capital T to capital T, therefore the limits will be minus t to t, and between this time interval the function takes on a value of a times cosine omega naught t, and therefore my integral becomes this. Next we can use the Euler's formula to write the cosine function in terms of complex exponentials, and therefore this particular integral can be written in terms of complex exponentials as this, which can be further simplified as this gives us this expression, and we'll now substitute the limits of t going from minus capital T to capital T. So once we substitute these limits, we can easily see that we'll get an expression that looks something like this. And note that the terms in the brackets can be written in terms of signs. So we can write this as a times sine omega minus omega naught t over omega minus omega naught plus a times sine omega plus omega naught t over omega plus omega naught. And this is the Fourier transform of our pulse modulated cosine function. And note that we can write this expression in terms of the sinc functions if we multiply and divide these two terms by t. Then we can write the Fourier transform of the pulse modulated cosine, where as sum of two sinc functions centered at frequencies of omega naught and minus omega naught. So this is our Fourier transform. So the Fourier transform of pulse modulated cosine function looks something like this. So the Fourier transform consists of two sinc functions, one at omega equals to omega naught and another having a peak at omega equals to minus omega naught. And the amplitude of the sinc functions is a times t. And note that the width of these sinc functions is inversely proportional to the value of capital T. So that means as I increase my value of T, that is half of the pulse duration of the pulse modulated cosine wave, that is shown over here. So as I increase this particular duration, these peaks will become narrow and narrow and their amplitude will keep on increasing. And we'll see that as t tends to infinity, that is the pulse modulated cosine function becomes the cosine function for times minus infinity to infinity in the limit of capital T tending to infinity. In that case, these sinc functions at frequencies of omega naught and minus omega naught will become infinitesimally narrow and their peak amplitude will increase to infinity while still having the area under the peaks equal to 1, and in that case we will recover the Fourier transform of the cosine function that is given by two delta functions at frequencies of omega naught and minus omega naught. Let us look at the Fourier transform of the pulse modulated cosine function for different values of the frequency omega naught and different values of capital T, which is half of the total pulse duration. So the pulse modulated cosine function given by this expression over here is plotted on the left hand side and its Fourier transform is plotted over here. So let us begin by looking at the effect of varying the duration of the pulse that goes from minus t to t. So we'll increase this duration of the pulse and see how the Fourier transform varies while keeping the value of omega naught, that is the frequency, fixed. So the pulse modulated cosine function we see takes on 0 value outside this interval minus capital T to t, and in between we have chosen the amplitude of this function to be 1. So in between we'll get a cosine omega naught t variation in between this time interval. And the Fourier transform of this function is given by two sinc functions centered at frequencies of minus omega naught and omega naught. And the amplitude of these sinc functions at these two locations is equal to capital T, and the width of these sinc functions is given by 2 pi over t, corresponding to the values where the sinc function takes the first values of 0. And now we'll see that as we increase the value of t, then my signal will better approximate the cosine function and the sinc functions will become narrow and the amplitudes will increase so that eventually I'll approach towards the Dirac delta functions. So this plot is for the case when t is equal to 2. Now, while keeping the value of omega naught to be fixed, if I increase the value of t to 5, then we see that the duration of the pulse is higher, but the width of these sinc functions in the frequency domain is smaller, and we expect this from the uncertainty principle, because if I increase my pulse duration, then the bandwidth should decrease. And in this particular case, note that the peak height has also increased because the peak height of the sinc functions is equal to t, and my value of t is 5. Now let's further increase the value of t, and in this case again the duration of the pulse has increased, and so has the amplitude of these sinc functions in the frequency domain, and the width of these sinc functions has decreased. And if I further increase the value of t to 20, we see that our pulse modulated cosine function now looks more and more closer to a cosine wave defined on the whole real line, that is between t going from minus infinity to infinity, and my sinc functions are now approaching the delta functions. And in the limit that t tends to infinity, these sinc functions will eventually give way to the Dirac delta functions at frequencies of minus omega naught and omega naught. So what we've seen is that we've started with a function that is absolutely integrable, that is the pulse modulated cosine function, and we know that the Fourier transforms are actually defined in classical sense only for absolutely integrable functions. And once we have this Fourier transform of this pulse modulated cosine function, we take the limit of t tending to infinity, then in that limit we obtain the Fourier transform of the cosine function, which otherwise we would not have been able to get because the cosine function is not absolutely integrable. This example of pulse modulated cosine function is also interesting because we can also vary the frequency omega naught while keeping the duration of the pulse to be fixed, and we can vary the value of omega naught. And note that in the limit of omega naught equal to 0, this function will become a rectangular pulse. So let us see what happens as we decrease the value of omega naught while keeping the duration of the pulse to be fixed. So at omega naught equals to 5 and t equals to 10, this is the Fourier transform. So we have again two sinc functions centered at frequencies of minus omega naught and omega naught. Now in this particular case my value of t is fixed, so the amplitude that is given by t is not going to change, but what is going to change is the location of the peaks that are at minus omega naught and omega naught. So let us decrease the value of omega naught, and now we see that these two peaks are closer to each other, and the signal has a smaller frequency within the time interval minus t to t because I have decreased the value of omega naught. Now if I further decrease the value of omega naught, then these two peaks in the Fourier transform will come even closer. So here is the Fourier transform and the signal for a smaller value of frequency, that is omega naught equal to 0.5, and my signal now looks like this. You note that the duration of the pulse is fixed, but my frequency is decreasing, and now we see that these two sinc functions are very close to each other, and their amplitudes are equal to 10 because the amplitude is equal to the value of t. Now if I further decrease the value of the frequency omega naught, these two peaks will merge. So this is what I get for omega naught of 0.1. So both sinc functions have now merged, although not completely, and therefore the amplitude has increased. And for omega naught equal to 0, we see that the pulse modulated cosine function is actually a rectangular pulse. And in this case, both the sinc functions have exactly merged and are overlapping with each other. Therefore, the amplitude is 2 times t, that is equal to 20, and we have a single peak that corresponds to the sinc function. So in this case, we have the Fourier transform is 2t times sinc of t times omega, because omega naught is equal to 0. So if we multiply and divide this expression by pi, we can write this as 2 pi times t over pi sinc of omega times t. And now note that if for this rectangular pulse, if I increase the pulse duration and take t tending to infinity, then this function, that is the sinc function with this particular amplitude, will tend to the delta function in the frequency space. So in the limit that t tends to infinity, you will get a delta function centered at omega equals to 0. And this is exactly what we saw, that for a function of f of t equals to constant value, the Fourier transform is equal to 2 pi times delta of omega. So this is another way in which you can think of how to obtain the Fourier transforms of non-integrable functions, where you start with a function defined over a finite time interval, and then you take the time interval tending to infinity, and you will get the Fourier transform in terms of the delta function. So now that we see why the Fourier transform of cosine functions and sine functions are represented by delta functions, we can now look at an arbitrary periodic signal and its Fourier transform. So recall that the Fourier transform of a complex exponential is given by 2 pi times the delta function centered at frequency of omega naught. Now let's say that I have a function that is periodic constant, and even if it is real valued, we can write in terms of complex exponentials using the complex form of the Fourier series. And here omega n is equal to 2 pi n over capital T, where T is the time period of the periodic signal. So any periodic signal we have seen can be written in terms of the complex form of the Fourier series, and now we have some arbitrary periodic signal f of t, and we are interested in the Fourier transform of this function f of t, that is periodic, and we can now see that it can be written as the Fourier transform of this complex form of the Fourier series. And because Fourier transform is linear, we can take the Fourier transform of individual terms in the summation, and we can write Fourier transform of individual terms. So here we should get Cn times 2 pi delta of omega minus omega n. So therefore the Fourier transform of an arbitrary periodic signal is given by 2 pi times summation of n going from minus infinity to infinity times Cn times the delta function centered at the frequency corresponding to the nth harmonic, that is 2 pi n by t. So what this expression says is that if you have an arbitrary periodic signal, let's say something like this, then its Fourier transform, and note that the Fourier transform will not be real valued in general, so we'll look at the magnitude of the Fourier transform, and then it will be composed of different delta functions corresponding to the discrete frequencies omega n. So a spectrum of a periodic signal will consist of discrete set of frequencies, and we know that these frequencies are integer multiples of the fundamental frequency omega naught. So this completes our discussion of the Fourier transform of sinusoidal functions. So we started with Fourier transform of sine and cosine through an example of pulse-modulated cosine function. We've shown how to intuitively think of why the Fourier transform of sinusoidal functions should be in terms of the Dirac delta function. And then what we've done is that if we have any periodic signal, then we can represent that in terms of the Fourier series, and then we can take the Fourier transform of that Fourier series, and in particular the individual terms in the Fourier series, and those terms would lead to the delta functions, and therefore the spectrum would consist of delta functions that are centered at frequencies corresponding to the integer multiples of the fundamental frequency. So this completes our discussion on the Fourier transform of sinusoidal functions.